welcome to our video on related rates. This will be our last little lesson in the derivatives unit, and next time we'll be getting into antiderivatives, and that will lead us into our last big section of content in the course. And I am preparing a new theme song for the videos. The song's pretty much done, but might need to make some minor fixes and make the video as well. That takes less time than the music. So related rates. This is an application of implicit differentiation, what we did last time. And these are real world problems. So if we have some variables, so let's say are related, by an equation, then it will follow that their derivatives are related as well, hence the name related rates. And there's often a time component to this, t being the primary variable. So I'll say variables are often implicitly related to time. So t is going to be our big variable for today. And we'll have both x and y often, or maybe other letters, which depend on t. So here are the broad steps for a related rates problem. Number one, if you don't have it already, find the relationship which is between the variables. Now, sometimes it's just given to you, and we'll see some of that. And I'll draw a picture, if possible or necessary. And those are more for the geometry type problems. Okay, step 2. We take the derivative with respect to time of both sides of our equation. So that's where implicit differentiation comes in. And that's how we'll get these related rates. And number 3, then we plug in what we know. We'll be given some specific information at a particular time, and so we'll want to plug in our stuff to figure out the missing variable. We solve for what we want. So, for example, let's say that x and y are functions of t. They depend on time. Then we want to find dy dt, the rate of change of y with respect to time, for the following relationship. So that's just given to us in this problem. And we need some particular conditions. So at this particular moment that we're looking at, dx dt is -2. and we're at x equals 2, y equals 4. So then given all that, we want to find dy dt in this moment. So step 1 is pretty much done for us already. The relationship was told to us. We got the equation. And a picture is not really necessary for this. We don't have a real world scenario set up. So in this case, we really begin with step 2. We take ddt of both sides of the equation. So derivative with respect to time of both sides. Now notice that t is my variable that I'm taking the derivative with respect to. So that means in this case, both x and y will be treated with implicit differentiation. You know, last time we we treated x as normal, but that was because I was taking the derivative with respect to x. So now there's a mismatch there as well. So what's going to happen is we take the derivative of x cubed, but we have to multiply by dx dt. Because, again, I'm taking the derivative with respect to time, not x. X depends on time, so that's why something's happening here. But then we just have to multiply by the derivative of x. That's chain rule. All right, and now we're treating y like we did last time. And, all right, let's factor out the 9. Both x and y are implicit functions of t. So let's take the derivative of the y part first. We're doing product rule here. So x times derivative of y plus derivative of x times y. Again, that's product rule. Okay. We could simplify here if we want. I don't think it's really necessary. I think we're at a good point where we can do step 3, where we plug in the particular information that was given to us. That would be these conditions here. At this particular time we're looking at dx dt is -2, x is 2, and y is 4. And that will then allow us to find dy dt at this instant. Right, let's zoom out a little. So 3x squared times dx dt plus 3y squared times dy dt equals 9 times 2 times dy dt. And dx dt is -2, y is 4. Right, so now we want to solve for dy dt, that's the point. So we'll simplify some things. This will be 12 times -2, so -24, plus 48 times dy dt. And now I'll go ahead and distribute this 9. So that'll give me 18 times dy dt. And there's this is a -8 here, times 9. So -72. We want the dy dt terms together and everything else on the other side. So I'm going to subtract the 18 dy dt from both sides. And add 24 to both sides. Those are my algebra steps. So that leaves us with 30 times dy dt equals negative 48. Just double checking my work there. Yep. Then divide both sides by 30. So negative 48 over 30. And that does reduce if you divide by 6. So there, this is the rate of change of y at this particular time. Now, this is a little more fun, I think, when we use actual real world examples. So we'll do a financial one and then a couple physics/geometry problems as well. But we'll start with the financial. So let's say the cost to manufacture X units of a product per month is given by C equals 0.2 x squared plus 10,000. So again, the relationship is given to us here between our variables. And the next problems that we do, it won't be that simple. But for now, we're given the relationship again. Then how fast is the cost per month changing? When I'm asking how fast is something changing, that's talking about a rate of change, a derivative. So how fast is the cost per month changing when production is changing at a rate of 11 units per month? And on top of that, the current production level is 70 units. All right, let's recap real quick. So the cost to produce X units of our product is given by this equation here. And then we're wanting to know how fast is this cost changing when we know how fast the production is changing per month. That's 11 units. And we know the current production level of 70. So we figured out the relationship. Well, it was told to us. And it's not necessary to draw a picture. That's not really going to help in this case. So we move on to step 2, where we take the derivative of both sides with respect to time, t. So derivative of cost equals derivative 0.2 x squared plus 10,000. So both c and x implicitly depend on time. They are changing over time, so they depend on t. So when I take the derivative of c with respect to time, I get dc dt. And we do power rule with the x. It's x to the first, but we have to multiply by dx dt because x is an implicit function of t. So we don't forget to multiply by the dx dt. And plus 0. Okay. So that's in a pretty good spot. Let's remind ourselves, what is the question asking? Well, here's the question. How fast is the cost per month changing? That's talking about dc dt. So I'm trying to find dc dt. So I need to know x and dx dt, and those were given to us at the end of the problem. So production is changing at a rate of 11 units per month. Well, that's describing how fast x is changing per month. That's 11. So dx dt is 11. And here I just multiply these two. The 2 times 0.2. X is 70 units. That's the current production level. X is the number of units. So 70. And again, the rate was 11. That's how much production was changing every month. And that brings us to 308. So $308 per month. That's how the cost is changing every month. So now a couple of physics-based problems, or geometry. It's really both. Well, let's say a rock is thrown into a pond, and this will create circular ripples outward. Okay, so those will move outward from the point of impact. And this will be so that the radius increases. After all, these ripples will get wider, they'll move farther out. So the radius of these circles increases at a rate of 3 feet per second. Question is find the rate at which the area is changing. That is the area of these ripples if you take the full circle. So in particular, how fast is the area changing at the instant when the radius is 17 feet? Right, we have to say this because the rate of change of the area depends on the time that you're at. It's not this constant rate of change necessarily. It will depend on our other variables. So that's why we need this extra information. We're talking about at a particular moment in time. What is the rate of change of the area of these circular ripples? Right, so you've got a rock. Maybe I'll draw a brown rock. Oh, it's not that way. There. Very beautiful rock. Okay, then outward from there, it's going to produce these circular ripples. Pretend that's a perfect circle. Let's make that a little better. Okay, still not perfect, but there we have our radius r. And that's really the only variable at play here besides time, of course, implicitly involved. So in this case, the formula was not immediately given to us, and that's pretty standard. So we have to figure that out. Our variables are area and radius. Which I'll call little r. And there's technically time as well, but I'm not going to write that. Because these are the things we need to relate. And time is implicitly related to these. So how do area and radius relate for a circle? Well, it's good to know that old formula. The area of a circle is a equals pi r squared. Pi being a particular number, which your calculator should have if you have a scientific calculator. So this is the relationship between area and radius of these circular ripples. And now we're ready to take d dt of both sides. So we have the derivative of area with respect to time. That's what we're trying to solve for. Pi is a constant, it's just a number. So it's left alone. But then we have r as a variable. R depends on time. So we take its derivative with 2r, but then we have to multiply by dr dt. That's implicit differentiation. Okay, so we want to look at the question again. We're trying to find the rate at which the area is changing. So that's dA dt. So I'm trying to find dA dt. So we're going to have to fill in this information here, both r and dr dt. Well, we're told the radius is increasing at a rate of 3 feet per second. So then that is dr dt. And we're looking at the particular moment when r is 17 feet. Of course, it's not like at all times r is 17 feet, but this is a particular instant. But that's what we're talking about. So plug in r is 17 feet. Radius is increasing at 3 feet per second. And so now we multiply this out, we'll need an approximation. We'll do 3 decimal places. Should get 320.442. And the units would be feet squared per second. Feet squared is area, and seconds is time. Right, that seems pretty fast now that I think about it. It's a pretty quick rate of expansion of the area. All right. Let's do one more. Another physics-related problem. Let's say we have a 10-foot ladder leaning against a wall. But in this scenario, the ladder is sliding down. The base of the ladder is sliding away from the wall, and that means also the top of the ladder is sliding down. We'll say the bottom of the ladder is 6 feet away from the wall. And we're talking about at a particular moment, of course, because that does change over time. Or I'll say, and is sliding. At a rate of 2 feet per minute. So it's a pretty steady, gradual sliding away. Then the question will be, how quickly is the top of the ladder sliding down the wall? So we know how quickly the bottom is sliding away with respect to the ground, but the question is how quickly is the top of the ladder sliding down? Now, there's definitely a relationship between this rate that the base is sliding away and the rate at which the top is going down the wall. These are related rates. Right, so how about we get a little picture together first, and then we can get our equation going that relates the variables to each other. Right, let's say I have a wall like this, and I've got my ladder leaning against it. Well, the ladder is 10 feet long, so I'll write that there. And at least at this present moment, it's 6 feet away. The base is 6 feet away from the wall. Now, I don't necessarily know this height here, but we can actually figure it out. And the other bit of info that we're told is how quickly the base of the ladder is sliding away. So that base is sliding away horizontally at 2 feet per minute. So as that happens, that means the ladder will also be sliding down the wall. The top part will be. And that's what the problem's asking about. So notice what shape this is forming. Let me draw it over here separately. This is a right triangle. Triangle with that 90-degree angle. Where the longest side, the hypotenuse, is 10 feet. And this horizontal part is 6. And this is also x, let's call it. It's not always 6, it's just 6 at this instant. And let's call the vertical distance y. So x and y are my real variables at play here. And those are related by the Pythagorean theorem for right triangles. Pythagorean theorem says that x squared plus y squared equals 10 squared, since 10 is the longest side. So you have this relationship with any right triangle, any triangle where you have a 90-degree angle like that. So here's their relationship. It wasn't given in the problem, we had to find it. And let's find the rates by taking the derivative of both sides with respect to time. And 10 squared is 100. Remember, for both of these, we're going to have to multiply by some derivative because of implicit differentiation. My variable is t. So for this first derivative, I get 2x times dx dt. And then for the y squared part, I get 2y times dy dt. And that equals 0. Now recall, the problem was talking about how quickly the top of the ladder is sliding down the wall. That is talking about the rate of y. And that's a rate of decrease in this case, because y is going down as the ladder slides down. So we're trying to solve for dy dt, and the rest of the information we're going to have to fill in. So I was told that at this instant, x is 6 feet. It's that horizontal distance. And we're told the rate of change of x, it's 2 feet per minute. Now this part might be a little bit confusing. I'm writing a positive 2 for dx dt instead of negative 2. Even though the way I drew my picture, x is moving to the left. But that's just due to the fact that the picture can be misleading. So we actually do not want dx dt to be negative in this case. We want positive 2 feet per minute. And that's because when you really think about it, what's happening to x as the ladder slides away? This horizontal distance x will be increasing. So that horizontal distance x gets larger over time as the ladder slides down. So indeed, dx dt is positive 2. So my picture was just a little misleading in that we're moving to the left in the x direction, but it's still the case that x is increasing, because x is this horizontal distance. So that matters because that's going to affect our final answer. Okay, so trying to find dy dt, I need to plug in y. Well, if we look in the problem, we're actually not going to find it. But it doesn't tell us how high up the ladder is at this point in time. But the trick here is that we can figure it out based on the other information. I know at this moment of time how far away the base of the ladder is, 6 feet. And I know how long the ladder is, 10 feet. And based on this relationship, the Pythagorean theorem, I can find y. So maybe I'll write that over here, at the top. Let's say when x is 6 at this particular moment, that means that 6 squared plus y squared equals 100. That's 10 squared. So y squared is 100 minus 36. 36 is 6 squared. So that is 64. And then take the square root. So that means when the base of the ladder is 6 feet away from the wall, based on how these relationships work, that means the top of the ladder must be 8 feet up the wall. So that's why we had to figure that out for ourselves. So sometimes you have to do that. And now we're finally ready to find dy dt. Right, so we get 24 plus 16 times dy dt equals 0. So subtract 24 from both sides. And when you divide by 16 and reduce, get negative 3/2. It's feet per minute. I would like to point out that this answer is negative. And let's make sure that that makes sense to us. So dy dt, that's the rate that height of the ladder up the wall is changing. And of course, in this problem, the ladder is sliding down. So that means, yes, in fact, y is decreasing as the ladder slides down the wall. So indeed, dy dt is supposed to be a negative number. So that makes sense. All right, I'll see you next time as we talk about antiderivatives. And so that will be our first steps into our final big unit on integration. And be prepared for a new theme song and intro.